Hello everyone, my name is Dominique Calder and I am a PhD student at George Mason University under the advisement of Dr. James Jones. And today I will be presenting on building and decaying a file corpus for subsector analysis. So currently, law enforcement and private organizations process massive amounts of data and digital evidence, sometimes up to petabytes with some organizations. And we often have to quickly determine if there is data of interest present on a device. Traditional file search methods are usually very time intensive and yield the best results when we have an exact match that's been identified. Files that have been partially overwritten tend to go undetected when we're searching via file hashes. So you may be wondering, what is a file hash? And a file hash is a way to verify the integrity of a file. The slightest change to the file would cause the file hash to change completely. And so though we have this integrity tracking mechanism, it makes it extremely difficult or nearly impossible to track files that are largely similar but share some differences. We have files and artifacts in digital investigations, and they often go unfound when file hashing is being used as a sole source of integrity matches, because that leaves the narrative to be partially misunderstood, and we have to continue to find more ways that we can tie our story together, find more artifacts that can tie our story together. And file hashing, while it is very great, it has proven ineffective when it comes to finding the most important artifacts. So here we have an example of what it looks like to hash the word or the phrase hello with an exclamation point. So we have here on the left two inputs that have hello with an exclamation point, and you can see on the right side, after they have gone through the SHA-256 hashing algorithm, that they produce the same hash. But when we remove the exclamation point at the third example on the left, it creates a completely different hash output once it's gone through the hashing algorithm. And so this is a perfect example of how the slightest change to a file can change a file completely. So if we were looking to see if we had something to the effect of hello with an exclamation point, that will go unfound during an investigation because the file hashes are completely different. So what we're proposing is to use a method what we call sector hashing, and that creates a unique digest of the data and is more granular than your traditional file hashing. We are able to take the sectors of a file instead of the file itself. We are breaking that file up into the little sectors that it is stored on the hard disk, and we're hashing those sectors to determine how a file is dispersed amongst the system. So we're using a public document corpus, GovDocs1, and it has about 1 million files. And we propose to generate sector hashes for each of those files. And this microscopic view creates a many to one correlation of each file given the associated sectors, and that enables forensic examiners to understand the data more granularly and also make more accurate determinations in that file's activity. So these research efforts aid potentially in identifying criminal networks, along with detecting anti-forensic and data tampering tactics. Our goal is to develop a scalable algorithm that can accurately infer the past presence of a file given arbitrary sectors. So the sector hash that's been ingested is split up into data blocks, and those data blocks are hashed given whichever hashing algorithm that we determine. And in our research, we used the MD5 algorithm, and we took a sliding window by hashing each sector and then hashing the sector next to it and the sector next to it all the way down the entire disk. Next, we want to choose statistically improbable features and feature combinations to search for within our sector hash blocks. And then we can analyze those blocks in small chunks via random sector sampling in order to determine, what potential matches we may have. Next, we want to determine a threshold criteria to evaluate our metrics for true and false positives and non-classifications, or what we call indeterminate, where we're unable to determine the matching criteria because there's not enough data available, for instance. We want to determine matches based off of our entropy score and distribution, our relative order, and similarity. So, for instance, if we have a file that has, maybe 8 or 10 or more of the same sector hashes present and they're in the same order, it's likely that they came from, say, the same file. Even though later on the file hashes may change, that just means maybe the files are, maybe one came from the other. One is a parent file of the other. And then we want to be able to iterate our algorithm and decay it incrementally by 10%. And this will show us how the files persist after file write events such as overwrites and deletes. And we can also determine how that entropy changes as well during those events. Here we have an example of a file from the GovDocs corpus, file 00001.doc. It is a file that is only 40 kilobytes, and where we would normally do file hashing, that would create one file hash for this file. In our proposed methodology, we are sector hashing this file, meaning we are chopping it up into small pieces, and then we are sector hashing those small pieces. So this 40 kilobyte file has created a sector hash combination of 10 sector hashes. Now, in contrast, a file that's 18 megabytes, that's significantly larger than this file, that file has created 3,460 file hashes. So that's a way more granular level to look at this particular file 00001, where we did not normally have that type of insight to determine this further information about this file. And in an example like this, as I was mentioning earlier about parent files, we may have a file that contains these same 10 sector hashes, but maybe that same file also contains another additional 10 sector hashes. Well, them being in the same order, in the same sequence, if you will, that will tell us that it's likely that these two files either came from each other, were created, maybe duplicated. And we can make a lot of assertions from there, but it is to show that these files are similar to some degree. Unlike file hashing, they would tell us that they are two complete different files because the file hash is completely different. And here's a more detailed understanding of what the decay algorithm looks like. So here we have the same data that we just saw previously for file 00001.doc, and here we have our levels of decay. So when we first built the GovDocs sector hash corpus, that is level decay 0. That is the ground truth of the GovDocs files, and they have not been touched or decayed or changed in any way. So this file, as you can see all the way down, we have a 0 for not decayed and 1 represents decayed. And so as the decay iterations go, we iterate every 10% and decay more and more. You can see how the file decay status changes, or the sector decay status changes over time. And so during file write events and things like that, we are unable to determine, how this file has changed, what parts of the sector have still, persisted over time, and, being able to see how the files decay over time, or maybe if it's only been decayed 10%, it's likely that we'll still have, a large chunk of this file still available to analyze. So this decay algorithm is very strong in helping us determine and understand what happens to the files as they begin to get overwritten and deleted. And we can also determine what happens to the entropy as the file decays. And when we mention entropy, we're talking about how random a file is. All of these characteristics together are the statistically improbable features that we talked about previously. And those features help us determine the matches for sectors in the future. So our present state right now, we have hashed all of the GovDocs corpus. As I said, it's approximately 1 million files, and they have been hashed at the sector level and put into a database for analysis. We have also began decay iterations in order to determine how those sectors persist after file overwrite and delete events. We are still currently analyzing the entropy of those files. So we are creating that ground truth for what is the entropy when we first created the GovDocs file hash corpus. And then we are going to track that entropy as we decay and run those different iterations, because the file's entropy will change as parts of it start to get deleted, for instance. Our future state would include some more in-depth details, for instance, how this research impacts traditional hard drives and what this research looks like when analyzed on a solid state drive, for instance. And ultimately, we would like to use this research to determine matches between diverse and dispersed data sets when using sector hashing. As I mentioned earlier, we have a huge problem in our investigation realm where we don't have enough data in order to make an accurate determination. And so in the future, we want to be able to fingerprint and almost do what we think of like DNA matching for these files. And we're going to use the grounds of this research to do that matching, to determine that one file inherently came from another file, or one file was at some time shared the data that is within another file. That is a much more accurate determination when we're creating that narrative and telling that story during an investigation. And here we have some references for the research that we've done thus far. We hope to continue with this research and really help advance the industry of digital forensics and digital investigations. So again, thank you everybody for your time, and I appreciate your time and attention today on this presentation. Take care.